Okay, in this video we're going to be looking more closely at delocalized versus localized lone pairs. And we're going to be looking at a couple of examples that are a little bit counterintuitive based on some of the information that we've already covered. So, as a little bit of a reminder, when we talk about electrons being delocalized, we're saying that they are participating in resonance. Right? Localized electrons are electrons that are not participating in resonance. Now, to be delocalized, a lone pair of electrons must be adjacent to an atom with an unhybridized p orbital, and also they must be in an unhybridized p orbital themselves. So, when I look at this Lewis structure, I have a lone pair, it's adjacent to this carbon is participating in a double bond, and so in order to form that pi bond, it must have an unhybridized p orbital, and so this lone pair should be delocalized. Now, when I look at the resonance structure I can draw, if we were to go back to chapter 1 and I was to say, okay, what is the molecular geometry and hybridization of this nitrogen, I probably would have said, well, it has 1, 2, 3 bonds, 1 lone pair. That's 4 electron groups. With 1 lone pair, that makes the molecular geometry trigonal pyramidal, and it's sp3 hybridized. If I was asked the same thing about this nitrogen, I'd have said, well, it has 1, 2, 3 electron groups, so it's trigonal planar and it's sp2 hybridized. Now, that can't happen. I can't have 2 different resonance structures for the same molecule with different hybridizations and different geometries, because it can't flop back and forth between the 2. So it's got to be one or the other. In order for this lone pair to participate in resonance, it must be in an unhybridized p orbital. Therefore, the hybridization of this nitrogen must be sp2, and it must be trigonal planar. That's the only way that it can participate in resonance. So, when we're assigning geometries and hybridizations for molecules that are participating in resonance, we have to be a little bit careful and be sure that we consider all of the resonance structures. In order for the molecule to participate in resonance, there must be an unhybridized p orbital. So this nitrogen can't be sp3. In this case, it must be sp2. So here's another example that's a little bit counterintuitive at first. If I was to give you this Lewis structure and say, draw me the resonance structures, I think it would have been very natural to say that, okay, well, we have a lone pair, it's allylic to a double bond, so I should be able to form the resonance structure indicated by those red arrows. Now, the problem is, right, this nitrogen is sp2 hybridized, right? I have 3 electron groups, but that unhybridized p orbital is already being used to form this double bond. That means the lone pair can't be in that unhybridized p orbital, and it must be in an sp orbital coming off the back, and because it's not in a p orbital, it can't be participating in resonance. So continuing from the last side, we can't just assume because a lone pair is delocalized just because it's allylic to a pi bond. As a general rule, if an atom possesses a pi bond and a lone pair, they can't both participate in resonance, and so that lone pair is going to be localized. Right? And as always, if there is no p orbital next door to the lone pair, then it's going to be localized. So if I look at the nitrogens in this compound, they all have a lone pair. They only drew the lone pair on this nitrogen, right? But both of these nitrogens are neutral. They both have 3 bonds. To be neutral, they must also have 1 lone pair. So this lone pair is not adjacent to any p orbitals, and so it's going to be localized. And this nitrogen would be sp3 like we'd normally predict. Now this nitrogen has a lone pair, right? And that lone pair is allylic to a double bond, but because the p orbital of this sp2 hybridized nitrogen is already participating in a double bond, that lone pair must be localized. So the nitrogen is sp2 hybridized, but that unhybridized p orbital is already being used to form this double bond, so the lone pair must be in an sp orbital, and it's going to be localized. Right? This nitrogen, its lone pair is allylic to a double bond, and it's not already using its p orbital, and so this lone pair is delocalized. in order to be delocalized, this nitrogen must be sp2 hybridized. All right, so one final example. If we wanted to identify each lone pair on the nitrogens as being localized or delocalized, right? The nitrogen out here doesn't fall into any of the patterns that we look for resonance, so it's going to be localized as we would normally expect. And then because I have 3 bonded atoms, I have the 1 lone pair, it's going to be localized. Right? This nitrogen, which we might have predicted to be sp3 hybridized, is adjacent to a p-orbital, and so I can form a resonance structure by moving this lone pair down here to make a double bond. I can then move this bonded pair of electrons up here to make a lone pair, and so this lone pair is delocalized. In order for that to happen, the nitrogen must be sp2 hybridized, and it must be trigonoplanar. Right? When I look at the lone pair on this nitrogen, it is allylic to a double bond, but because the p-orbital is already involved in the double bond, right, this lone pair is going to be localized. So it is sp2 because it has to be forming this double bond, but because the unhybridized p-orbital is already being used for this double bond, it's not available for the lone pair, and the lone pair is going to be localized.